Welcome Year 9s, and I'd just like to say well done to all of you who showed up for this webinar. For those of you who are logging in later, obviously it's still really important because all of your work for each week will be based on each of these PowerPoints that are being delivered. So I'm going to be delivering the Year 9 PowerPoints on Tuesdays, and that'll be at 1 o'clock obviously. And they're going to last for about 30 minutes to 40 minutes, depending on how many questions you might have at the end of it and how quickly I manage to get through the topics. So today, obviously, we're starting off on energy, and I've given this sort of a subtitle of leading to P2 because one of the major factors that they bring up in the AQA syllabus is that all of the equations and the understanding of energy is really important to be able to answer questions in P2. And in fact, you will be asked to use some of the equations in P2 as well. So all those equations that you would have learnt, or hopefully would have learnt since the start of Year 9, they can also be used in some of the P2 exam papers. So, gave you some starter questions to start off with here. Some of you might find these easier than others, but the name 3 energy stores is the first question there. The second question being, what do we measure energy in? So another form of that question would be, what are the units of energy? And that's something you need to be aware of. So that's the same question there, really. What are the units of energy and what do we measure energy in? That's the same question. Question 3, which store of energy will be in a moving tennis ball? The important key word there being moving. So I'm going to let you guys have a little think about that whilst I just show you what our success criteria is going to be on here. And as Mr. Lamb had sort of explained at the start there will be an opportunity for you guys to be asking questions in the Q&A box, but also there's going to be 4 different multiple choice polls that I'm going to give you throughout this presentation. And just as a heads up, for each of these polls, if you're on a mobile device, they will take over the entire screen and you'll get the 4 choices to choose from. And some of you might find that you don't actually get the polls there at all, because maybe your device isn't synced up to it or something. We're not entirely sure why that is yet. We're going to be working that out, hopefully have it fixed by next week. But so the polls are going to come through when I post them. And it's just a sort of way of checking your current understanding so I can move on in the topic. And yeah, so you'll see those when they come up. Right, so answers to the starter questions there. 3 energy stores. I gave you gravitational potential. We've also got elastic potential energy in there. We've got nuclear, there's kinetic, chemical, thermal, and electrostatic. And we're going to be looking at some examples of those energy stores as we move through the slides today. We're not going to go into the equations to calculate those today, but we are going to be looking at, sorry, I should have showed you this on the success criteria really. We're going to be looking at the conservation of energy, and we're going to be looking at the calculation for efficiency. So back to the starter questions there. We had the question 2 as the units for energy is joules. You can just write that with a capital J, but you have to be understanding that that is joules. Question 3, the store of energy in a moving tennis ball could be kinetic, okay, because it's the moving energy. If I threw it upwards, obviously that kinetic energy would be transferring into gravitational potential energy. But it's the moving keyword, as I was saying there, that is going to tick you off to say that it's kinetic energy. Right.
Mr. Brown, sorry, can I just interrupt? A couple of people have asked if it's possible for you to turn your microphone up. I think for some people, you're a little bit quiet.
Okay, I'm going to try and just hold it here. Is that better? Is that louder?
Yes, it is.
It's, right, I'm going to do this sort of like string technique with my microphone here and see if that works out. If there's any other comments like that, Mr. Lamb, I'll try and sort something else out. So please let me know if it's still a real trouble for them. Right, so energy stores. Now, I like to use these kind of visual displays for energy stores because it really helps me to understand what each of the stores are displaying or which type of objects or substances they might be found in. Okay, so obviously elastic potential, classic example of that is an elastic band, right? But you would also find elastic potential in loads of different objects, okay? So in a tennis ball, if you squeeze a tennis ball in, it springs back to its original form if it's not broken. And that initial push in is an example of elastic potential energy because it's got the potential to spring back to its original shape. Magnetic energy, pretty self-explanatory. Electrostatic gets a little bit more confusing. The big example they've used there is obviously the clouds with the lightning. Basically, it's any form of potential difference between static energy. So you've got examples being the thunder clouds, the lightning clouds, but also we talk about electrostatic energy in an electrical circuit as well. Thermal energy, that's pretty self-explanatory again. People sometimes write heat energy. It's really important that you write thermal energy, okay? In GCSE, you may not be awarded the mark for writing heat, so write thermal energy. Gravitational potential energy, again, this is a type of energy where the higher you put an object, the more gravitational potential energy it will get because it's further away from Earth's center of gravity, okay? Now, the last one obviously being kinetic. In any moving object, that will have a store of kinetic energy. Okay, and it's important to realize that all of these are stores of energy. So we can look at transfers of energy in a separate PowerPoint, but for today we're just interested in these stores, and then we're going to be looking at how they do actually transfer from one store to the other, and we're going to talk about that in terms of the conservation of energy in a moment's time as well. Now, here's some examples again, right? So I've given the examples of all of the different types of energy there on the left. We've got the thermal, elastic, gravitational, kinetic, electrostatic, chemical, magnetic, and nuclear. And we've got some examples there as well, okay? So in these examples, you've got things like kinetic energy, anything that's moving. Gravitational potential energy, something that's high up, a book on a shelf, okay? It's really important that if you're looking at any object, that you're aware of perhaps what type of energies that it might have stores of and what type of energies it might be able to transfer that energy into, okay? So multiple choice. This is where I've got to use this poll thing. Hold on one sec. I might have to zip back over here to use it. Polls. So the first poll, I'm going to launch this poll for you. I'm going to read it out for those of you that may not be able to access this poll. So question 1 is, which one of these is not a store of energy? And I can see you're already putting all your answers in there, guys. Really good. So the answers are, is it gravitational potential energy that is not a store of energy? Is it joules? Is it chemical? Or is it kinetic, which is not a store of energy? Which of those is not a store of energy?
Mr. Brown, while the students are answering that, I've had 2 questions that I think are useful for everybody. One was how the students get the slides and answer the question on the questions on the slides, and that's come from a few people who perhaps weren't here at the very beginning, and a few people have mentioned that they can't actually see the poll, so perhaps going back over that for people might be useful.
Yeah, sure. Thanks, sir. So first of all, let me just quickly reiterate the fact that we are setting this PowerPoint. I'm going to be talking through the PowerPoint with you. Any of the questions which show up, which I'm expecting you to answer today, will be in the form of the polls. For any of you who can't access the polls, just answer it in your head. It's not really essential that you have to answer the poll. It's just useful for me and Sir so that we can get an idea as to what everyone's generally putting. Okay, so that we get a better assessment as to what you think the answer is. That's why we're using the polls. If you don't see the poll in front of you, don't worry. We'll carry on with the presentation. Just try and answer this question in your head. So here's the question again. Which one of these is not a store of energy? Is it A, gravitational potential? Is it B, joules? Is it C, chemical? Or is it D, kinetic? So which one of those was not a store of energy? So with any of the questions that I put up in this PowerPoint, as I said, I'll be putting out a poll if I want you to answer them now. But all of the other questions, the follow-up questions, you'll do in your own time after the PowerPoint. So we're not expecting you to look at the questions on the screen and answer it instantly. You'll only have to do that if it's in the shape of or form of a poll. These are my words there. Does that make sense? I can't hear you, but that's good. Right, so I'm going to end the poll there. Give me 1 second. I'm still learning with this thing, guys. So, oh, and fantastic. Still getting 1 or 2 still going in, but that's fantastic, guys. The overwhelming winner at the end of that poll was, of course, joules. So we measure energy in joules. It is not a store of energy, okay? And I've got the option to share results there, but I'm not going to do that at the moment because I'm going to carry on with the slides. So carrying on from here, multiple choice 1 that we've just done. So energy transfers. So in fact, actually, we've just done the first success criteria. We've just looked at that, recalling energy stores and giving an example, okay? And now we're looking at energy transfers. So in the energy transfers, it's really important that you understand the different stores and the examples that we were going through earlier, because they might ask you to refer to an energy transfer that has occurred. So what store of energy to begin with has changed into which store of energy after, okay? So as it says here, energy can be transformed from one store to another. Energy transfers usually involve changing one store of energy into more than one store of energy. And that's usually because the other stores of energy are more chaotic. One of the most common stores of energy, which is wasted energy, is thermal energy. And you can think of examples of that all over the place. Like in a car, if you're trying to slow down a car, you're applying a force to the brakes, which is transferring the kinetic energy of the moving car into thermal energy. But we don't want our tires to be warm. We're not going to go around afterwards and warm our hands up on the tires. That is a wasted store of energy. So an example here is the gravitational energy in a ball is transferred into kinetic energy when it is falling. Cool. Now, I've got a few more examples that we're going to go through because I'm going to have another multiple choice question for you after these. So this one here, this example is, or the question even is, what energy transfers are wind turbines in a wind farm designed to carry out? Now, we know that they are collecting or trying to transfer the wind energy, right, which is actually the movement of air particles. So moving energy, we know it's kinetic. So the wind, the kinetic energy from the wind is going to be transferred into an electrostatic store. Okay, that's the one I was talking about earlier in the circuits. The electrostatic store is then obviously transferred through an electrical circuit, and it will probably have another function in one of your homes or in a workplace or in an industry. Okay, so it's constantly being transferred from one to another. Kinetic energy in the wind transferring to electrostatic store. In a petrol engine, this is slightly different. So we've got in the petrol engine here, the store of energy. We know that we top up our cars with petrol. That's what allows them to run, or diesel. And that petrol is a chemical. So the chemical energy there is being transferred to an electrostatic store again in the engine, as that's powering the motor and making it move. So we've got a transfer of energy occurring there, going from the chemical store to the electrostatic store. In this example here, hydroelectric power station. Now, these are really great, okay, because hydroelectric power stations are quite a mechanical thing, really, again. Water's quite high up. The water being high in a dam is going to have a higher gravitational potential energy store than it would at the bottom. And in fact, actually, you could even argue a step in between with this one. The gravitational energy store is falling through the dam. And in that case, it's actually moving. So again, you could argue that kinetic energy would be the product of this gravitational store. However, that kinetic energy is pretty much immediately going to be turning a turbine in the dam, and that's going to again generate an electrostatic store, transfer even, from the gravitational store to kinetic to electrostatic. So we're getting a few transfers occurring there. And this is going to lead us on to this multiple choice question 2 here, where I'm going to give you a few different
Hello, Mr. Brown. Can you hear me?
Oh, sorry. I have no idea what happened there, but you've still got my screen up, so that's good. Can you hear me still? I'm sure you can. Hopefully you can.
I can hear you, Mr. Brown.
Lovely, Mr. Nam. I'm very sorry about that. My computer just froze and then shut me out. So give me 1 second to quickly get the slides back up. And if you've got the session running there, actually, it should still have that on record. So you just have a blank space for a minute or so. Sorry.
Yep. Hi, everyone. We will get it back in just a second.
Yeah,
Thank
it won't
you.
be long. 1 second. Terribly sorry. And then I'll send out the poll to you. Actually, I can send out the poll now, thinking about it. And then, oh, I don't have the polling option. Do you have a polling option there, sir?
Yeah, I do. Which poll is it?
Send out poll 2 for them. And then I'll get onto it.
There you go, everyone.
And do you need to make me the host again or something like that?
Probably. I'm going to have to find you in attendees. It doesn't give me that option. I think you already are.
Oh, okay. I'll just kind of look.
Yep.
Okay.
Thank you for going with us, everyone.
Yeah, it's all good. I've got it here. I might need to get you to do the polling because I can't flip between the screen like I did before. I think something might have happened with that. Right, where am I? This one. Okay, and you've got my screen now, have you? I think so. Right.
I can see you now. Yep.
Lovely, 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 lovely. Okay, so the polling question there, for those of you who didn't get the screen shared. So I asked you to name the energy transfers taking place when a match is lit, as in one from a matchbox. So the option A is it transferring from kinetic store to a thermal store? Or is it B, thermal to kinetic store? Or is it C, transferring from chemical store to a thermal store? Or is it D, transferring? I won't give you very long for that because I timed out and we need to move on. So the answer for question 2, let me just quickly check your polls if I can. Oh no, Sir's got that option. So the answer to question 2 for the poll was C. It is a chemical store to a thermal store. So there's a chemical in the match that obviously, when ignited, releases the thermal energy in the match. Okay, so that's converting the chemical store to the thermal store. So we, half of us sort of went for the top answer. And, you know, you could argue that you're striking the match, you're creating that kinetic energy there as well in order to transfer the chemical in the match to the thermal. But generally, because the match is made of wood and it's got the phosphorus tip, we would talk about that being a chemical that's going to convert into the thermal energy store. So well done to those of you who got that one right. So I'm going to swiftly move on to the conservation of energy. So in this part of the success criteria, we are going to be describing conservation of energy, and most of you will be able to repeat the statement of conservation of energy. And it's, if you've learned the conservation of mass in chemistry, it's pretty much the same principle. So generally it's stating that energy can neither be created nor destroyed. It's only ever transferred from one store to another. Okay, and the amazing thing about this, the thing that I love about this, is that what this means is that all the energy that makes up our universe, everything that we see interacting with each other around us today, in the past, in the future, will and has always been here. Since the start of time with the Big Bang, all of the energy that was in that tiny singularity exploded outwards and has formed the universe as we know it. So I just think that is an amazing, amazing fact. And the reason why that's so important is because it actually tells us that energy doesn't get created or destroyed. It doesn't come from nowhere. It's transferred from one form to another, from one store to another. Okay, like we've seen already in the match, it was stored as chemical energy in the match. When struck, that chemical energy transferred to thermal energy. But say I started with 10 joules in the match of chemical energy, I wouldn't be able to get any more than 10 joules of thermal energy outwards. And in fact, you'd rarely, actually, I don't think you ever get a transfer that is 100% efficient like that. Some of the thermal energy will also have been transferred into things like kinetic energy as the heat rises, so on and so forth. So what I'm saying is you won't get any extra energy from it. It will transfer from one store to another with the entire amount. So this brings me to my third multiple choice. Now, I'm aware of the fact that I'm running through these multiple choices quite quickly now. In this third multiple choice, it's just a simple statement to test your understanding of conservation of energy. And that statement is, which statement is incorrect? So A, energy can be created. B, energy can't be destroyed. C, energy can be transferred. Or D, you can't make energy. Which of those is correct? And thank you for polling that for me, sir. I'll read that again to you for anyone who can't see the poll there. So question 3, which statement is incorrect? Is it A, energy can be created? B, energy can't be destroyed? C, energy can be transferred? Or D, you can't make energy? Oh, I get the option to have a guess myself now that Sarah's posted them.
Hello, sir. While people are answering that one, a couple of people have asked me the same question about the match, about how a match can have chemical energy. They didn't understand why it wasn't kinetic.
Okay, good question. So in a match, we're aware of the fact that plant matter, animal matter, are all carbon-based life forms, okay? They're actually often made up of a lot of carbon, hydrogen, and they're quite useful fuels. So in a match itself, the chemicals which make up that match, mostly old cellulose and things like that from the plant matter, those chemicals, when reacted with oxygen, can release that thermal energy. Okay, so it's transferring from the chemical store in the bonds between the molecules in the match into thermal energy as it's recombining and bonding with oxygen. Does that make sense? Does that answer it for you, sir, as well there?
Yep, think so. Yep.
Okay. So, are the polls in? Have we got our polls?
Yes.
Lovely. So, obviously, the answer to that one, with which is incorrect, it's not so obvious actually. It's a little bit of a tricky question I've given you there. The answer is A. Energy can be created is incorrect. We can't make energy. Okay, so the last one was right. Energy can't be destroyed. Good. And energy can be transferred. Good. So the one that was incorrect is A. So efficiency. Now, I want to get a little bit of maths in here. And efficiency is a lovely calculation because this is stuff that you guys have done since year 7, really, in terms of percentages. Right? If you ever want to work out the percentage that you've got on a test paper, you take the marks you've got and the total marks, divide the marks you've got by your total marks, and then times it by 100. Okay, there you worked out the percentage that you've got correct in a test paper. This is exactly the same equation, really. So it says here, first of all, I should explain what efficiency is. If we're talking about a device and saying that it's very efficient, what we mean is that it's converting a lot of its energy, its initial energy, into useful energy. It's efficient at what it's doing, okay? So in a few examples that we're going to go through, you'll see what useful energies are and wasted energies are. I'll give you a quick example. So if I've got a speaker and I'm transferring some electrostatic energy into kinetic energy to make the speaker move, that speaker wants to move. That's what we want it to do. So that's the useful energy, the kinetic energy. But it might also create some friction, which would create some thermal energy. Now, again, just like with the car tire earlier, you're not going to stand around a speaker and try to get warm. That's wasted energy. We don't need that energy at all. So it's important to understand what useful energy is for a device and wasted energy is for a device. They're not always the same thing. For example, a heater, an electric heater, the useful energy in that heater is thermal energy. Okay? We want the heat from that heater. However, wasted energy in a heater could be something like kinetic energy. Vibrates, you can hear that, sending out some sound waves. Don't need that from a heater. We don't want the ambience created by a heater. We just want the heat from it. So it's important to recognize what useful and wasted energies are. That can then be inputted into this equation. And as I said, we've done percentages for a long time. It's as simple as a percentage. So we should also be aware to rearrange equations. I'm going to go over that towards the end of this video because there's a couple of examples about rearranging equations. I still quite like using triangles for simple equations like this, but obviously you can use the mathematical method as well. So I'm going to give some examples. It's important to, actually I'm going to talk through the equation first because I haven't actually noted what it is. Again, efficiency equals useful energy transferred by the device divided by the total energy supplied by the device, okay? And then if you wanted that as a percentage, times it by 100. So in this case, we've got an electric motor being used to raise an object. This transfers 60 joules of useful energy. So I'm going to put that up top, 60 joules of useful energy. When it's supplied with 200 joules of electrical energy. So I've got 60 divided by 200. I'm just going to do this now on my calculator just to show you. Some of you will be shouting the answer to me in my over the screen. So we've got an answer of 0.3. And I'm going to times that by 100 to work out our efficiency in a percentage. So it's 30%. Okay, let's do another one. In this one, it says an electric motor is used to raise an object. It transfers 150 joules of thermal energy when it is supplied with 250 joules of electrical energy. Calculate the efficiency of the motor. Now, I specifically changed this question, put this in, because I wanted to make it clear that it's really important to identify the useful and the wasted energy. Okay, so it says the total, actually, first it says the transfers of 150 joules of thermal energy. In a motor using to raise an object, we're not interested in thermal energy, that's the wasted energy. So we're going to assume that the leftover energy is going to be the useful energy. So the total put in was 250 joules. And if we minus 150, we're left with 100 joules, which must be the useful energy. So now I do the same equation I did from the last one. I do 100 joules, and I divide that by the total energy put in, 250. And simply put that into my calculator. You can always use a calculator in science. This is why I became a science teacher, not a maths teacher. That's only a joke. Science is just way better. And so I've got 100 joules divided by 250, and then times that by 100, I've got 40% for that second question. Okay, so it's, as I said, it's really important to realize there that it's important to know what the useful energy is in this example. Okay, so let's try example 3. Now this one is the rearrangement of the equation that I was talking about before, and you can do it in a couple of different ways. So we've got 75% efficient fan. When it's supplied with 250 joules of electrical energy, again, when it's saying electrical energy here, it means electrostatic. Okay, so it's when it's supplied with 250 joules of electrostatic energy, calculate the useful energy input of the fan. So we want to know how much energy of the 250 joules is transferring to the useful store. Okay, so again, we're going to do a similar rearrange. We're going to rearrange it slightly this time. So now what I'm going to be doing is I'm going to be dividing my total energy by the 75%. Okay, actually, originally it would divide that by 100. Okay, 250 divided by 100 and times by 75. And that should give us the answer. 1 second. I will just get this 250 times by 75. Okay, so 75% of 250, you can also do this in a variety of different methods. Like originally, if I was trying to find a percentage of a number, I would probably times 75%. Sorry, do the 250 by 0.75. No, give me the answer there. But the method I've shown you is 250 divided by 100, and then we're going to times that by the percentage. So it gives us 187.5 joules of useful energy. Okay, that's the useful energy output of a 75% efficient fan, which has been supplied with 250 joules of energy. Now, I'm aware of the fact that I've literally dotted around that quite a lot. It might not make loads of sense. Go through it slowly with the examples that I'm going to give you in a moment, and hopefully you will be able to get the correct answers. Now, there is also a whiteboard function on this, which I'm going to hopefully get into use with Mr. Lamb next week, so that when we do an example of an equation, it might be able to see easier my working through it there. Anyway, we're on to multiple choice 4, and this comes from this question up the top here. So I'm going to ask you to answer this question as part of the multiple choice. But I want you to use that equation. If you haven't got that down in front of you, can everyone please just write down this equation first? So can you write down efficiency equals useful energy transferred by the device divided by total energy supplied to the device. And then I also should have put times by 100 to get it in a percentage. Soz, guys. So if you've got that equation down in front of you, fantastic, because I'm going to ask you to do this multiple choice question now. And again, for those of you who don't have the poll coming up in front of you, if Miss Lamb, if possibly she'd shut that. You're a top man. Nice one. So the question 4 is calculate the efficiency of this device. So we've got 160 joules of electrostatic energy is converted to 40 joules of light and 120 joules of thermal energy. So you need to calculate the efficiency of that device. Remember, you do useful energy divided by total energy input and times it by 100. It's really good, guys. It's lovely actually seeing all of your votes going in from the calculations. I'm not expecting you to do it instantly as well. Some people get flustered if they think they've got to do maths really quickly. Sort of throws them off. So we'll give you another 20 seconds or so to get this done. I said I'm not going to rush you, and then I'll just give you 20 seconds. And then I'm going to just talk you through the last practice questions and things that you've got at the end of this PowerPoint. And
so
yes.
Sorry to interrupt you. A couple of people have asked, they understand the question here, but they weren't sure which one was useful because they weren't sure what the device was.
That is an incredibly good point. Okay. I'm sorry, guys. I should have told you that this is a lamp that we're using. So yeah, it's a lamp that I've written in my question from before, but I didn't send that to Mr. Lamb. So terribly sorry about that, but you may have caused a bit of confusion. So let me just reiterate the question. In a lamp, 160 joules of electrostatic energy is converted to 40 joules of light and 120 joules of thermal energy. Calculate the efficiency of this device. Is it A, 25%? Is it B, 30%? Is it C, 75%? Or is it D, 70%? Yeah, and I also was just going to reiterate as well, because I think there's been a bit of confusion with some of the other years as to how much of this you're expected to complete, guys. So obviously, as with any of our work that we've been setting over the past few months, it's really important to understand that it is good to keep up with the work, but if you reach a point where you've been doing it for 2 to 3 hours long and you're not making any headway, then that's the time to call it quits. Or if you haven't spoken to your teacher already, that's the point when you should be or should have already spoken to them and asked them to help you through with the work. So in these PowerPoints, for example, the tasks that you're expected to do are to log in or to watch it after this session and to go through and practice the polls when I give them to you, to take notes if you want to, but you will have access to the PowerPoint at home, so you can go through that and revise that as well. At the end of each of these PowerPoints, there'll be a set number of questions, could be calculations, could be short answer questions. Sometimes there'll probably be exam style questions as well, because it's really good practice to practice some of those. And then you'll send those back into your teachers and they can mark them through for you. If they set different work, that's absolutely fine, but you will always have some work each week from the slides which I'm going to present and the questions which I'll leave for you at the end of it. So just to reiterate that for anyone who may have just joined in or anything. So thank you, sir. I think we'll close the poll there as well. I'll end that poll. And yeah, lovely. We've got a majority there with the correct answer. As I said, it can be tricky in these polls to get your answers correct under time pressures. But that's also good practice as well, sometimes to go and give yourself a bit of a time limit, because they're the kinds of things sometimes that you'll be facing in an exam. So we have just calculated that it was, in fact, 25% for the useful energy and the efficiency there. So that was really good, guys. The majority of you got that correct. And there's a couple of follow-up questions here as well, which, as I said to you just a moment ago, I'm expecting you to answer these questions. And for the students in my class, you'll have a copy of this PowerPoint sent into the Google Classroom. You just need to make a copy as you normally do, and then hand that in on the Google Classroom with the answers there. There's not just these practice questions though, I'm afraid. You're not going to get off that easily. We've got this table, which I'd like you to fill out as well. In this table, obviously, it's really important to notice in the device, what is the useful energy going to be? So for the electric drill, it's got kinetic, sound and heat. As we said, we're not going to stand around a drill trying to keep warm. That's not what a drill's for. We're not going to listen to the dulcet tones of our drills, because that's not what drills are for. They're useful for drilling holes, which is movement, obviously. Okay, so got the table to complete there as well, guys. And then finally, some follow-up questions. So these questions are what I'm expecting people in my class anyway to be going off and completing now. And that does apply to everyone else's classes as well. As I said, it's also just really important to look in your Google Classroom to check to see if your teacher has given you perhaps maybe another smaller task or a slight variation of these slides that I'm showing you now. Okay, so I think we're going to end very shortly. If there's any other questions which Mr. Lamb has picked up in the time being, I'd happily stay on and answer any of those if I can now. If not, you can obviously email your teachers to clarify that, but it is better to do it now because you might have to wait a while for an email from the teacher. Quite busy.
The only question that's appeared really, Mr. Brown, because you've covered everything, the people were asking about how they get the slides, so those will be in their Google Classrooms. There will be a record. We did record this and it will be available as well if you need to watch it back. You'll have all of the slides. People have asked when the work is due, sir.
Good question. So at the end of the week is the general approach. So for me, for example, I'm going to put a sort of deadline on it on as Thursday, because that's a good few days of time to work through the work. And then it also gives me that opportunity on the Friday to have a look through your work and mark them before next week. But generally, by the end of the week is a good time, and it gives you a bit of time then to maybe formulate a question for the next session, or to speak to your tutor, your teacher over this week and clarify any of the misconceptions which you may have gathered or anything. Does that answer your question? Sure.
Yeah, I think that's all of the questions we've had, sir. I'd just like to thank so many of, someone's just popped up. Are we meant to be able to see Mr. Lamb? Yes, I enabled my video so I could talk to you all.
Oh, you did.
And I've got some questions. People are saying, is this all of the work for the week? The answer to that is yes. I think when you go back and have a look at it, when I say this is all the work for the week, the questions on there and the practice questions on there are your work for this week. Actually going through all of those questions might take you a little bit longer perhaps than you think. So what will happen now is today, each of your teachers will share these slides on your Google Classroom. Your work is then to go through the slides and actually write all of the answers on them as you go through and turn it in to your teacher. And then there will be another webinar to explain next week's work at the same time next week. I think that answers the questions I've got popping up there.
Seems good.
And I'd just like to say, I mean, you can't all see how many people came, but more than half of Year 9 are here. We had 130 people at one point. So fantastic to see you all here. I
Yeah,
hope
good
it
stuff, guys.
was you are all now free to go. You do actually need to leave because I'm going to stay and talk to Mr. Brown. So if you haven't left in the next couple of minutes, I will be dropping you out of the room. So bye, everyone, and have a fantastic week.
Yeah, well done, guys. Cheerio.
Got a couple left.
Yeah.
Just wait for them to drop out.
Yeah.